Very good morning to all of you. And I'm very happy today because this is a workshop which is under IOE initiative. And we have a special guests from US, Dr. Nestor. And Dr. Nestor is well known, but in the interest of audience, let me introduce briefly. Actually, I have about 6 pages of CV. I'm not going to read out everything. But let me just briefly tell you about his background. Dr. Nestor obtained his PhD from University of Illinois, Urbana in 1978. And he has been the senior scientist of microscopy in Argonne National Lab from 2005 till date. And he's also a scientific director and group leader, Electron Microscopy Center from 1984 to 1994. And he's also a scientist in Electron Microscopy Center from 1983 to 2005. And he's also an engagement in Oak Ridge National Lab from 1978 to present. And he has got several university appointments. I'll just mention a few of them. He's a senior fellow, Consortium for Advanced Science and Engineering, University of Chicago from 2018 to till date. And he's a senior fellow from Northwestern Argonne Institute for Science and Engineering. And he's also a senior fellow of Computational Institute, University of Chicago. And he's also visiting professors, positions in several universities, importantly, University of Manchester, Northern Illinois University, University of Illinois at Chicago, Cambridge University, Urbana-Champaign, and Illinois Institute of Technology in Chicago. So, Dr. Nestor has got several professional honors and awards. The list is quite long, and I'm not going to read everything.
Good. You can stop there.
And some of them, with the latest ones, at least I'll mention, in 2023, he has been recognized with the David Cockheim AMMS Award and Guinness World Record Award in 2022. And almost every year he has got an award. So it's a very illustrious career, and I'm extremely happy and privileged that he is here to conduct this workshop. And thank you, Dr. Nestor. The floor is yours. Maybe I'll request Ravi to share a few words, because he is also, he can mention about our institute initiative about this, so that we could do all this.
Thank you very much for bringing Dr. Nestor here, and I'm told in the afternoon Dr. Hamish Fraser also will be here. It's a pleasure to have you, Dr. Nestor. You must be knowing that IIT Madras has heavily invested in microscopy, electron microscopy, and we have state-of-the-art characterization facilities in the institute. Yes. And electron microscopy is being led by Dr. Shankaran. Certainly we have a lot of interest in electron microscopy, and IIT Madras was named as an Institute of Eminence by the Government of India. And that scheme, several centers were approved, and one of the centers that were approved to be established is an Institute of Eminence Center on Electron Microscopy, Advanced Microscopy. Mm-hmm. So he has invited you under that center to offer lectures. So we are very happy that he has brought some esteemed and highly qualified people who can engage the students with basic concepts to advanced concepts in microscopy. I think I don't have to say much, because when you started your microscopy career, I was just a 3-year-old baby opening up my eyes to see how the world looks like. So I think you have phenomenal experience in
Markham.
Yeah. But if it is that, then mine is much smaller at a nanoscopy scale. So I would welcome you once again. So I hope you will have a nice time interacting with the students here, and we will meet again in the afternoon after my class. I'm teaching right now, so I will meet you again.
Better get going.
I'll do that.
Nandri.
Yeah.
Thank
you.
Vankanam. Yeah. Thank you again, everyone. It's my pleasure to be here. It's my pleasure to return to IIT, because I got my bachelor's degree at IIT. IIT in Chicago, not IIT in Madrid. Slightly different name, but the initials are the same. So, today is going to be an interesting day. As I was telling everybody a few moments ago, this is a workshop. It's not a lecture. I'm not here to just talk to you. I will. But the important thing, and maybe even for our remote audience, can they send in questions, email you? Okay, if you have a question, you should stop me and ask the question, okay? Because if you have a question, it needs an answer. If it's a really long question, maybe we'll put it off for a little bit, but if relatively short questions or something, a clarification, we should do that. The challenge that I have is to try to cover a lot of material in just 2.5 days. We will not succeed, okay? To tell you that ahead of time. But everything that I present today will be available as a PDF that I'll give to with it, and you can all have a copy of it, okay? It will all be public domain information. You can share it both for your own notes and share it with colleagues, okay? So, just to give you a sense of what we're going to talk about first, let's see if I'm going to go backwards for a moment. So what we're going to talk about today is a variety of things. I'm going to start talking first in general about EM in general and materials, just to give you a few examples of the kind of things we do. Then, because we've got a wide audience here, some of you know electron microscopy fairly well, other you need a refresher, and some people will be novices. So I'm going to spend some time talking, let's see if I can use this. Does this work? Yes. We'll talk first a little bit about challenges and some examples and materials, and then I'm going to talk about the basic instrumentation. Okay? My purpose is the following. If you don't understand the basic instrumentation, then you don't understand how to use it to solve different problems. I don't want you to go away today or this week and just say, all I have to do is push a button and I will get an answer. If that's the message you get, I failed. The message today is let's understand how we detect something, how we measure something, and then how we analyze the data to get quantitative results to answer a question. The important thing is what's the question you're trying to ask? How do we then make a measurement to get the answer to that question? What resources are needed? And what experiments might you need to do to answer that question? Now, during the course of the next few days, we're going to talk about a lot of different techniques. It's not just an electron microscope. What we have in reality is an instrument that I call an electron optical beamline. Those of you know about beamlines at synchrotrons, right? A microscope is no different. There's a source, an accelerator, optics to bring a beam to a target, scattering from the target and detectors that surround it. It's a beamline. And some of our beamlines, modern electron microscopes, are actually cost as much as a normal beamline in a synchrotron. Their beamlines are fairly simple. It's just a straight tube with a beam. We have a lot more complicated factors to deal with. All right. Then after lunch, we're going to talk a little bit about electron diffraction first, or diffraction phenomena. I'll start it off, and then Hamish will jump in and add some more. Tomorrow, we'll talk about elastic scattering, mainly imaging, okay? Both conventional TEM and scanning transmission, and dynamical theory and diffraction contrast, some imaging. After lunch, I'll talk about inelastic scattering, which is actually my forte, the thing I get most interested in, and how we use inelastic scattering also to characterize our sample. Finally, in the last day, we're going to have some, depending on what the audience is interested in, we'll talk about other topics that we can add. Radiation damage, chemical imaging, in situ microscopy, different aspects. And I'll base that based on you. If nobody's here interested in situ, we won't talk about in situ. If you're interested in radiation damage, we'll do that. Maybe we can get Hamish to talk a bit on computationally mediated microscopy. All of that is relevant, so we'll play it by ear. And then in the end, we'll have an open question and answer session. And there, what I would like you to do is think about the work you're doing or the problems that you're trying to study right now and say, I have the problem. Here's my problem. What would you do? And We probably don't know the answers, but we can at least give you some direction. Okay, so let's move forward. First thing I want to do is obviously acknowledge I work at Argonne. Most of my work is supported by the U.S. Department of Energy and at Argonne National Lab. I have a lot of colleagues that have contributed to a lot of the slides I've had over the years, and they make a huge list, okay? And I can't remember them all, because my slides I've been collecting for years, so I thank them all, and I apologize to any of them on my list that I've forgotten to put their name down. Again, anybody wants a photo, those of you in the audience watching remotely, we are going to have the lecture notes. Every slide that I present over the next few days will be converted into a PDF, and you'll be able to get a copy of that, and you can share that. So it will be freely available. Okay, let's talk for a minute about materials research today. What do we do? What do we do? We're interested in new materials and phenomena. What we try to do is we create new things. We discover and explore to try to understand them. We control these materials, and we apply them to solve problems in today's society. What's our motivation? Well, there's a lot. There's also a national strategic need. Doesn't matter what nation you're in, everybody has a need to do something. We're all focused on energy and the economy today. Health is important. There is some work on defense for everybody. And really, the thing that gets me excited is not so much is enabling other science. What can I do to help somebody else to let them do their science? All of that is important today. Okay? Let's ask ourselves, what's the basic question that we all ask? Well, we ask ourselves, what does it look like? What's the state of the material? What's its morphology, its shape? Is it crystallographic? Is there crystallography involved? What are the elemental and chemical constituents of what we're looking at? Is there bonding? Can we tell some information about that? What's the electronic structure? It depends on the problem you're doing. We also have evolved. In the past, we did everything statically. We'd look at something and it was there. It was effectively dead, nothing moving. Today, that's no longer the problem. In today's evolved technological environment, we want to watch things dynamically. We want to see things change. We want to understand what's making the change. And what are those dynamic processes? Well, it could be just a change with time, could be a change with temperature, stress or strain. Those of you that are mechanical engineering know quite a bit about that. We want to look at different environments. We don't want to look at things in vacuum. We don't exist in vacuum. Most materials don't. What happens when we change the environment? What happens when we put an electromagnetic field of some type on it? And is there an irradiation environment? And there's two reasons for radiation environment. It's not just nuclear materials. It's satellites in space. They're in an irradiation environment. We need to know what damage happens there. So that irradiation environment could be charged particles, could be photons, could be almost anything. And what are our challenges? The challenges today is to do all of this in real-time processes. We want to watch things happening. Let's see now. I think this guy should, if I push the button, there we go. Go. We want to watch things changing. We watch things moving. I want you to watch this process. These are actually particles in a liquid in the TEM. Okay? We watch particle growth, particle coalescence. We want to understand what's happening. And you can see not only are they moving, but they're coalescing, they're ripening, getting larger. How can we do that? We want to do high spatial resolution analysis, and we'll be talking about later in the week. We also want today to do simultaneous imaging of both hard and soft materials, polymers and metals, ceramics and biological materials. So all of that, knowing the relationship between those. We want to do it dynamically. What I'm showing you there, that little video clip was slow. We might want to do it faster because we want to watch a dynamic process that's happening rapidly, or maybe we want to do it slowly. Okay, so that's what we'd like to do. Now, what are the basic questions that most investigators ask? Well, they tend to ask, what does it look like? How big is it? Okay. What's it made out of? Where are the important bits? And I always get this one. That's not what I expected. It shouldn't look like that. Okay. So we want to watch things going on, and we want to explain that. Ask yourself, what are the limiting factors? So you have an opportunity here. One of the opportunities is the barrier to entry. Well, here at IIT Madras, you've got resources that are available for you to do that. So your barrier to entry is a little bit lower than somebody that doesn't exist at a university like Madras. There is some bureaucracy. You're going to have to do some paperwork. You have to be a student or a researcher. You have to find money to do it, or somebody has to find money to get the resources here. Nicely, the department's done that for you, or at least some of it. You need staff. It's not just you running the instrument. There's research staff associated with it that has to help you. You need access. You need the ability to get to it. And there are also barriers to getting results. Okay? The most important barrier to getting any result with any electron microscope, any investigation, make sure you know your specimen. You should be spending as much time understanding your specimen and making your specimen as you do everything else. Because in the US we have the saying, garbage in is garbage out. Okay? We need expertise. That's why you're here at the university, to get some expertise. You have the advantages of local experts that can help you to do things, and expert staff. And you need the infrastructure and instrumentation. And again, you've got some very nice tools here, resources, to do that. All right. What are today's challenges? I'll give you the big picture now first. I'm going to start out with the big picture, and then we're going to work around. The big picture is multimodal analytical sensitivity at the sub-nanometer to sub-angstrom resolution ladder in both hard and soft matter. So what do I mean by that? I mean, well, we're going to be looking at materials. Here's an example of a complex engineering material. It happens to be a catalyst. Actually, that's not the catalyst. That's the support. That's basically cerium oxide. The catalyst, if you can see them, they're small, very little tiny white dots there. That happens to be, and now you see them in red, the ruthenium, which is the catalyst. So the cerium oxide in blue is the support. The ruthenium in red is the catalyst, and that's the thing we're interested in. So how do we know where it's there? We have to use a subsidiary or other analytical processes to see them. It's not just catalysts. Everybody's worried about water today. Okay? This is a polyamide membrane. It's used in water filtration. What do filters do? They take out of the water contaminants. Okay? Can we see? Well, we see little things in here. Okay? This happens to be a complex folded membrane, and it's absorbing materials. How do we know it's absorbing? Well, we get these white areas. What are those white areas? Again, during the course of the day, we'll learn that those white areas can be analyzed, and we can tell that those happen to be transition metals that are acquired on the membrane surface. Biological systems. This is a photocatalyst to help convert CO to water, and from the water we get hydrogen and oxygen, so we got energy. Okay? This is a thacalolide. Okay? It's from the surface of a cyanobacteria, which we find all around the world. These naturally take CO and convert oxygen, convert hydrogen, create water. What we want to do is enhance the productivity of it. We found out that if you add noble metals, in this case platinum, to the thacaloids, that the enhanced catalytic activity happens. Well, where does it go? Well, we see lots of white dots again. That we assume is platinum. Well, yes, can we see the platinum nanocrystals? Yes, we can see. If I blow a layer up like that, we see the platinum nanocrystals, but that's not the important thing. What's important are these tiny white dots, which are single atoms of platinum sitting there. Those are what's helping do the catalytic process. Okay, and at some cases, now that's supposed to be a video. Let's see if I can get that to work. Where is the button? Certainly in the machine you have here, the aberration-corrected imaging machine, this came from an aberration-corrected imaging machine, we're looking at the edge of a single crystal, and what are we watching? Oops. if we watch that, let's see if I can get it to play a second time. We see single atoms, and watch very closely, single atoms moving along that surface. What's happening there? Why are they moving? How do we get these images? How do we analyze that? That's some of the work we're going to be talking about here. Okay, and we want to do all of that in real time. And I'm sure all of you would say, oh, gee, I just want to make my sample, put it in a microscope, push a button, and get an image. That doesn't work, okay? If you don't understand the machine, the technique, all you're going to do is waste your time and waste time on the instrument. So I'm going to spend a lot of time talking about the instrument so you understand it, techniques to use to understand the images you use, and then toward the end we'll talk about how we analyze the data. So I will spend a lot of time talking about the instrument itself. All right, now, what kind of research opportunities are there? Let's talk about that for a minute. These are 7 themes that to me are important in today's technology. The nanoscale origin of macroscopic properties. Those of you that are in mechanical engineering, material science, you're always interested in the macroscopic properties. Well, those macroscopic properties, and depending on what you want, for example, structural materials, turbine engines, any of that, understanding how the structure and the properties of that relate to the nanoscale structure of a material important. The role of individual atoms and dopants, that's good, that's important in semiconductor technology, catalysts, quantum materials, quantum computing nowadays, it's all single atom. Characterization of interfaces at arbitrary orientations, ordered and disordered materials, probing materials in the native environment, okay? The in situ microscopy. Things do not exist always in vacuum. They exist in water, in air, in liquids. We need to understand that. Material far from equilibrium. And then for those, this is something more of an interest to me, conformal mapping of materials in electromagnetic fields. All of these are problems that we need to learn how to address. So there are a lot of scientific opportunities for everybody, and you can look at them, and again, this has to do mainly with what I'm interested in, but some of you will be able to pick out things within this that you'll be interested in, okay? And these opportunities represent technical challenges, not just for the measurement, but also for understanding the problem, okay? And what do we want to do with this? We want to do it quantitatively. We want to do it sometimes at the atomic scale, not always, but a lot. We want to do it in real time, okay? You'll hear that theme coming up. Ideally, in a lot of these, we want to do it in situ. So we want to do it not in vacuum, not in an unknown environment, but we want to put it in a real environment. And what we have to ask here, or the challenge that we're going to try to address in this next couple of days, is how do we use the electron optical beam lines in a way that augments traditional instruments to answer these questions? Okay, let's see. All right, let me give you a few examples of that now before we actually start talking about instrumentation. So high performance materials, defects in interfaces are important. Whether we're looking at dislocations in a high strength metal alloy with precipitation where we're stopping the dislocations, whether we're looking at grain boundaries or interfaces, or are we looking at semiconductor devices where the electrical properties are controlled by what's happening right at the interface. I already gave you this example just in a previous slide, catalysts for performing energy production. Nanomaterials are prevalent in almost everything you do. I'm sure there's a lot of people in the audience, not necessarily here, either here in the room or those of you that are listening remotely, that are interested in nanoparticles. What are the challenges there? Crystallography at the atomic scale, 3D imaging and diffraction, in situ controlled in controlled environments. Again, nanomaterials created. These are the metal oxide framework structures. We see nice little organic cubes that are formed. You see that nice organic cube. The interesting thing is when we look at that in the center of this cube that's grown, we see a framework that consists of platinum, and in the center is nickel. So it's a structure that's being formed electrochemically, okay? But it has unique properties. We didn't know where things were. We're using advanced microscopy techniques today, we can tell that. Okay. perovskites. I don't know if somebody the other day was asking me, are perovskites interesting? Of course they're interesting. They're engineered materials. This is a layered structure that doesn't exist naturally. It's been man-made. Okay? It's been man-made because in this particular case, it has unique ferroelectric modes. So studying ferroelectricity, for doing phenomenon. And if we look at this, we say, oh, that's an interesting thing, but let's look very closely. What exactly are these phases? What do we see? Well, if we go and look, I'm going to back up a slide for a second. We're going to blow up a region of this. Okay? And I'm going the wrong way. Blow up a region of this, and we can see the atomic layered structure of barium oxide, titanium oxide, barium oxide. At least we think that's what it is. The nice thing that we can do today is the modern analytical instruments can actually measure that. This is a color-coded image, and this is actually an elemental composition distribution. The green is the calcium, the yellow is the titanium, and the red is the barium. And when we looked across that very long strip here, we noticed there are changes across there. If I go across it, I can actually map out the elemental changes or distribution across that. And this is a line trace across here. The wiggles that you see are real. Okay? We're seeing the, let's see now, I got to look at the color code here. The titanium distribution, elemental distribution across the planes. The barium, the calcium, you notice the barium and calcium oscillate. The titanium goes through everything. And down across here is the support material that's grown in, the strontium titanate and the strontium titanium ruthenium oxide. So we can characterize all of that and now begin to understand what's going on. Catalysts, materials in real environments. I showed you a brief view before. Here you're looking at nanoparticles in liquid in a TEM. Okay? In the past, nobody would ever have thought of putting liquids in a TEM. You can't do that. Well, we can today. We'll talk about how to do that later. Okay. And for those of you from the biotechnology audience, if there's a few of you out in the audience, studying cancer, nanotechnology has been used quite a bit nowadays in cancer. These are two full-blown cancer cells. They've grown together, and we see structures inside that. You see, this is a pseudo-tomogram. We're tilting the sample back and forth. We can see the structures. With modern analytical techniques, I can tell you that, yes, there's my carbon, oxygen, phosphorus, and the like, but importantly, we see the transition metal components in there, mainly the titanium and the iron and a little bit of the phosphorus. So there's a reaction going in there. Those transition metals in biological systems are extremely important. Okay, soft and hard matter. Again, there may be members of the audience that are working with polymers. Polymers are a challenge, but they're also very useful because we can grow them, they self-assemble, and they can be used in a lot of different processes. So looking at the differences between the structures in polymer fullerene structures and the electrical transport across those, all things that we can do today. Okay, so, this slide appeared a second time. I see I've got it in the wrong spot. This is where it is. So our challenge is this. We talked about that already, so I'm going to skip forward that slide. We've done this one already. All right. Enough of an introduction to give you a flavor of the kind of things we're going to do. So what I'm going to spend some time now is we're going to talk about instrumentation. Because I want you to understand the basic instruments and how they work. Because once we understand the basic instruments, we can take our step forward going forward. So there are basically several kinds of microscopes today. There are microscopes that have lenses. Okay? An optical microscope is the classic example. I'm sure all of you have at some point in your career, whether in grammar school, high school, or as an undergraduate or graduate student, used an optical microscope. Very valuable tool. You can't get rid of them. Then there are the electron microscopes. There are also X-ray microscopes. And there's actually a neutron microscope, but a neutron microscope is designed to look at a railroad train or a truck. So would you call it a microscope? Well, not really. It's not micro, it's macro. Let's call it a macroscope, okay? Then there are microscopes without lenses, okay? Field ion microscopes have no lenses. Point projection microscopes, scanning probe microscopy, scanning probe microscopes. We're going to deal, oops, sorry, back up. We're going to mainly deal with microscopes with lenses, and I'm going to be focusing in on electron sources or electron microscopes today. And for those of you that came in late, all of the slides that you're going to see over the next few days will be available as a PDF, so you'll be able to take things away with you.
So on the way we were seeing that.
Okay, good enough. Okay, so let's back up. So there are two kinds of signals that we look at. We can either look at the reflection or scanning microscopes, and they look mainly at the surfaces, they do look a little bit, and transmission microscopes mainly deal with the internal structure. Modern instruments today can work in both modes, certainly in the TEM environments. We're going to mainly concern ourselves today with simple, with transmission modes. Okay. Now, various beam lines, and we talked about lots of different beam lines. We talked about optical beam lines, X-ray beam lines, neutron beam lines, all have resolution limits and capabilities. So now let's think a bit about what we want to look at. So let's look at different structures and see how big they are. Okay. So what's the classical object that you use to study something? Somebody. What do you call this? Your eyes. What's the resolution limit of your eye? Okay. Okay, good. Let's see if I got the right slide. Yeah, what I call is your personal beam line. You all have your own beam line. Some of us have aberration correctors for our beam lines. I didn't always have this, but after a little while you might need one too. So the typical resolution of your personal beam line is about 1/10 of a millimeter, 100 microns. So what can you see with that? You can see protozoa. Okay? Now, optical instruments give you some magnification. They allow us to see something smaller. Optical instruments take us down to, depending on the wavelength of light that we use, about 1/2 micron. Okay? We can see blood cells, bacteria. It's not good enough to see viruses. Okay? We go to X-ray beam lines, X-ray synchrotron sources. They have probe sizes that can get down to, if you believe everybody, they're just putting in a new beam line at Argonne. The synchrotron at Argonne just shut down last week because they're installing a new beam line. They'll be able to get to maybe 30 nanometers. Okay? But if you really want to go all the way down to the angstrom level, you need an electron beam line. Okay? So the object during the course of the day is to talk about electron microscopy and microanalysis. Okay, because we're doing characterization. We're not just doing imaging. So microscopes have traditionally been talked about for imaging and a little bit for diffraction. What I'm also going to be talking about today, which is my personal expertise, is spectroscopy. I use all of these to characterize a material. I'll spend a bunch of time on tomorrow talking more about the spectroscopy part of it, because that augments things. Just to give you a sense of history, electrons have been around for a while, right? J.J. Thomson discovered the electron in 1897. Okay? Through the years, I've highlighted a few things. The first EM was built in 31. Okay? Took about 8 years to get from the first electron beam line to get 10 nanometers resolution. Now, remember, I just told you, just in the previous slide, that the synchrotron at Argonne is about to go to 30 nanometers. Well, we had 30 nanometers back in the 30s. Okay? Now, over the years, we've gone a little bit better. We've gone from 10 to 1. Albert Crew in the late 60s had the first real atomic resolution electron microscope. Okay? 1999, we broke the 1 angstrom barrier. Okay? And in 10 years after that, we broke the half angstrom barrier. And nowadays, we're doing even more. We're doing high resolution spectroscopy and imaging. Okay? Now, let's compare, for your benefit, different beamline sources. Let's compare neutrons, X-rays, and electrons, okay? Because you'll have all of those useful in the kind of research you do. What do you want to do with neutrons? First of all, they're all very bright. Electrons are the brightest. Brightness is a measure of number of particles per centimeter per eV, okay? This is important, the elastic mean free path. How far in a material does a beam have to go before it interacts with matter? So neutrons, as you know, can go through everything. That's why they're used for looking through trucks and car engines and stuff. Have a mean free path of 10 to the 7th nanometers. Okay. X-rays are a lot shorter, 10 to the 3 nanometers. Electrons have a mean free path of 10 nanometers. Okay. What's the absorption path length? And that's how far do you have to go before something starts happening? Neutrons go enormous distances, 10 to the 8th nanometers. X-rays a little further. Electrons are very correct. So electrons are strongly interacting with materials. Okay. And here's the important thing, depending on what's the problem you're trying to solve. How small of a probe can you make? So with neutrons, your probe size is something like 10 to the 6 nanometers. X-rays, maybe 30. And electrons, we can get sub-angstrom nowadays. Okay, the other thing to worry about is the information about the specimen. All information that we get about a specimen has to do with the interaction of our source, whatever it is, and the specimen. And there are two kinds of interactions, two kinds of scattering events. There's an elastic scattering event and an inelastic scattering event. An elastic scattering event means our particle, whatever it is, in the case of EM, it's an electron beam, but X-rays is a photon, neutrons, it's a neutron. An elastic scattering event, the particle interacts and loses almost no energy. It may change direction, but it loses no energy. That's the basis for a lot of imaging work that we do today and a lot of diffraction work. So we'll talk a lot about elastic scattering. Inelastic scattering, the particle loses energy, or it changes direction, or it could be doing both. And again, we'll talk a bit about that because both of those techniques give us information about the solid, and both of those allow us to characterize something very precisely. Okay, so the question that I want you to think about today is, how do we use these scattering processes to characterize modern materials, to characterize the problems that we're interested in? Okay, and what are the limitations of those? We'll talk about both of those. Okay, so what kind of scattering can we see? In elastic scattering, there's a lot of techniques that we're going to be talking about today. We're going to try, and I'll emphasize try, to cover all the things in red. Okay, phase contrast imaging, amplitude diffraction contrast, select various diffractions, high resolution imaging. We'll cover most of those. We're not going to have, certainly not, we probably won't even finish all of these. We're certainly not going to have time to talk about these. We'll talk a bit about scanning transmission. That goes in hand in hand with transmission. We're not going to be talking about SEM. That's a whole nother lecture series. And we're not going to talk about some of the high energy reflection. Oops. So just to remind you, in SEM, we look mainly at surfaces. We can be looking at organic materials, inorganic materials, fabricated devices, and we can get some diffraction effects. In transmission microscopy, we do the same. We can look at organic materials or inorganic materials. So we can look at polymers, nanomaterials, organic structures in diffraction. We can look at grain boundaries, dislocations. We can do high resolution imaging, and we can do advanced diffraction. So we're going to concentrate mainly on this in the next couple of days. Let's give you a couple of examples of that. And again, I will pick from different things. In the life sciences, we can look at cells. So here's a whole cell that we're looking through. We can see the structure of the cell. In a polymer, this is a black copolymer, so there's actually two different polymer species here. I call these the fingerprint patterns. We have one is PMMA and one is PCM. We can look at structures that are grown, nanostructures. We can look at dislocations in materials. How do we analyze all these images? And we can look at very complex things. Okay? Here's a material. It's a man-made engineered material. We go through multiple phases. And the question is, what's going on in each of these phases? Those are the questions we're going to ask ourselves and how to do it. We're going to look at defects in materials and learn how to analyze the defects in materials. This is something that's a very old image. It's part of my PhD thesis back almost 50 years ago. How do you analyze the dislocation structure? We'll talk about that. We'll look at high resolution imaging. This is a calcium titanate layer. And what we're seeing is this is an atomic resolution imaging. There's a scale bar. Oh, here we go. A scale bar here when we're looking the spacing between individual atoms. And we see changes in that spacing. We also see rotations of the octahedra in there. Okay? All of that has to do with how the material is grown and what its properties are. And then we have what I call nanoparticle soup. Somebody will walk up to you, or you may actually end up with it. You'll come up with something that is, you go, what the heck is this? Okay, we're looking at, can anybody tell me what that is? Well, there's long things and round things, and big things and little things. Your challenge will be to use the resources that are available to you, whether it's an optical microscope, an electron microscope, an X-ray scattering system, to analyze a structure like that. Okay, it's not going to be simple, but you can do it. And we're going to do that using not only elastic scattering spectroscopies, but inelastic scattering spectroscopies. So I mentioned all the stuff we do with elastic. Those were examples of elastic imaging. In inelastic scattering, we have lots of different signals. We can have an incident electron coming in, and we measure an electron coming out. Okay? Those are generally the electron loss spectroscopy techniques. We can have an incident electron coming in and a photon coming out. Those are the X-ray emission spectroscopies. We can have a photon coming in and an electron coming out. Those are the photoelectron processes. And then we can have the X-ray absorption spectroscopy, so photon in and a photon out. So we're not going to talk at all about these. We'll talk a little bit about the X-ray and electron loss spectroscopies. Okay, and what do those spectroscopies look like? They look like an electron microscope with detectors on them. We're going to talk a lot about the two different detectors. You can analyze those. And both of these give us different information about the solid. X-ray spectroscopy tells us one thing, electron loss spectroscopy tells us something else. Are they complementary? Absolutely. And I hope you're going to see that in the course of a few days. What can we do with some of these analytical spectroscopies? Well, we can look at something like this, a grain boundary in a piece of steel. I can say it's a grain boundary. What's important about this particular grain boundary? It exists. But more importantly, this happened to be a intergranular stress corrosion cracking problem. And an intergranular stress corrosion cracking was happening right at the grain boundaries. And the question is why? Well, we can form an image, and there's nothing really outstanding about that image, right? Well, there's a grain here and a grain here, and there's our grain boundary. What's special about that grain boundary? Why does this grain boundary break and other ones not? That's where we need more than just the elastic image, which is what this is. We're going to go to the inelastic scattering spectroscopies. We're going to go to that grain boundary, blow it up a little bit, and I'm going to take my now electron probe and walk across that grain boundary and measure the composition across that grain boundary. And if we look at this, the composition of the blue, which is the nickel, is uniform. But the composition of the iron and the chromium changes. Why is that grain boundary weaker? We've got a depletion of the iron and an increase of the chromium at that grain boundary. That's why the material fails. Now, different question is, how do we stop that? That's part of your research project, how one determines what's causing it. First, you have to know what the problem is, cracking. Then we have to do a measurement to figure out, is there something significant about that? Yes, we got a change in the composition of the grain boundary. Okay, then the next thing is, how do we answer that question? That's another research project, right? Okay, I'm going to skip that slide. Okay, enough of an introduction. So I've given you an overview of the sort of things that we're going to talk about. Covered a lot of ground, okay? So now we're going to stop talking about global things, feel-good things, motherhood statements about, hey, you can do this, you can do that. You're going to say, well, how do I actually do that? And that's what we're going to spend now. I'm going to spend the rest of the morning talking purely about the instrument, okay? We're not talking about how to analyze data. Just talk about the instrument. I want you to understand how an electron microscope works and what's important about it. Because when you sit down in front of that instrument, I want you to be able to say, oh yes, I know what I'm doing right now. I know I have to do X, Y, Z, and this is how I got it. Okay, so the first thing to talk about is some fundamental properties of electrons. Okay. We have an electron, okay? And the electron is, sorry, I'm going to back up a little bit. We're going to have an electron source. It's going to go down through some lenses to hit a sample, and then more lenses to form an image. So we're going to walk our way through the electron microscope now. Okay? So first thing to realize, electrons have certain characteristics. They have certain energies, and they have a certain characteristic wavelength, okay, lambda. Okay? That wavelength is determined by the accelerating voltage of the microscope, and you should always remember that when we talk about the accelerating voltage of the microscope, everybody says, I have a microscope that runs at 30 kV or 60 kV or 100 kV or 200 kV or 300 kV. That's just the accelerating voltage. That's not necessarily the energy of the electron beam. Okay? Because when we start going from something relatively low in energy, 10, 20, 30 kV, those are relatively low energy electrons. As we start going up to 100, 200, 300, or even 1,000,000 volts, now we're starting to get to electrons that are relativistic. So there are relativistic corrections that you have to do always. Okay? Just to give you a sense of that, as a function of accelerating voltage, this is the wavelength of the electron as a function of accelerating voltage. And I've highlighted some key areas here because, let's see now, you've got a 300 kV Titan here, right? Okay. So the characteristic wavelength that we have for your electron beam here, you look at the wavelength here in terms of angstroms. It's well sub-angstrom, okay? That doesn't mean this is the resolution you get, but this is an important parameter to know. So knowing the wavelength of the electron for your different energy instrument operations is important. Okay, so all microscopes use lenses, and all microscopes have the same characteristics. They have an illumination source. In this case, if you have an optical microscope, it's light. We have lenses that bring the illumination to the specimen. Then we have magnifying lenses, and then we have some kind of detector. Okay, so we're going to work our way through that. Okay, so that was an optical microscope. This is what a transmission microscope looks like. So sorry, I've now flipped things upside down for you. So we've got a source, okay? We've got accelerator to bring that electron beam to a certain energy. It's focused by lenses to a specimen. Electrons or light or whatever is scattered from the specimen, goes through additional lenses, and goes to some sort of detector. This is a real electron microscope cut in half. It's a bit of an old one. It's an old RCA EMU3, and we physically cut it in half. It actually took 3 microscopes to be cut in half to make this. It's difficult to do, but I want you to get a sense of what's going through it. And we're going to look at the individual components. So we have an electron gun. So at some points at the very top, so let me back up. So I'm going to show you pictures of different sections here. So we have the electron gun. So we got a high voltage cable in that brings our high voltage in to a very small filament that's heated, and that's our electron source, and the electrons go out. They come down the column through various lenses. We'll talk about lenses in a moment. What you have is pole pieces surrounded by copper wire. We run current through the wire to create an electromagnetic field, which focuses our beam down through the column, eventually hits some sort of detector. This is a very old microscope. You can see it's been around for a long time. It had a fluorescent screen. That's back when we used to look at fluorescent screens, or when I used to look at fluorescent screens. And the detector then was a fluorescent screen and your eyeball looking at it, and when we wanted to record something, we put a sheet of film down underneath and lifted up the screen. I don't think your machine has film in it anymore, does it? No. You still have a camera, though? Yeah. Okay. Okay, what about the electron sources? What kind of electron sources are there? There's actually 3 types. There's a piece of tungsten wire called a tungsten hairpin. Okay? It's literally a piece of wire, very thin. We heat it up. We run current through it. It heats up, glows red hot, and the glowing process, it's emitting light, but it's also releasing electrons. Okay? There's the lanthanum hexaboride type filaments. That's also a slightly heated filament, and but it's also a partial field emitter. We'll talk about that for a minute. Electrons come off from the tip, and then there's the field emission sources that you'll have in your machine downstairs. Do you have an XFEG or a cold FEG? XFEG, okay. Okay, thermionic sources are fairly simple. It's a piece of wire that we heat up to a certain temperature, and we get current that comes off of it. Okay? The amount of current that we get is proportional to the temperature. So you want more current, what do? You turn up the wick. The problem is when you turn the wick up too much, what happens? You melt the wire. So typical failure of a tungsten filament is you've melted it. Okay, you've heated it up too long. Eventually, however, remember, even if you don't overheat it, but you're just heating it up and leaving it, slowly the metal is coming off. Okay, you're slowly evaporating the tungsten, and these filaments always fail. Okay, they will always fail, and there will always be a break. Okay, is that good? Yeah, no, we don't really want it failing because that means we've got to stop and change the filament. How long they last? It depends on how well you use the instrument. Do you have any tungsten filament machines here? You do. SAMs mainly.
When the lab 6 goes, then we use tungsten filament.
You use tungsten, okay. Tungsten's fairly cheap in dollars. For US dollars, I don't know what it would be in Indian rupees, right? But dollars, $20 a filament, roughly on that order, okay? 2,000 rupees, is that right? No. $20 would be 20,000 rupees, okay. Relatively inexpensive in that thing. The other type of filament, and there's different types. There's the bent hairpin, sharp ones. LAB6 is another filament. It's lanthanum hexaboride. It's a crystal that is a partial field emitter. If we heat them up a little bit, they give off even more electrons. They're very nice, very coherent sources. They're also very expensive. If this guy is $20, this guy's $1,000. Okay? So you want to be more careful with these guys. And as we've just heard, if the LAB6 goes out, you replace it with a tungsten until you get another LAB6. Okay? The third type is the field emission source. Okay? The field emission source is literally a single crystal, usually of tungsten, sharpened to a very sharp point. Very rare. They are sometimes slightly heated. There's both cold field emission and heated field emission. They rely on electron emission just by putting a large potential between the tip and an anode, and we get a field emission source coming out. Electrons are literally ripped out of solid. Okay? They're very nice, they're very small probes, they're very expensive systems. Okay? Replacing a field emission tip is an expensive process. You don't want to burn them out too often. But they do last. I've had a field emission tip running for 3 years. Now, I'm pretty careful with it. And I'm sure that the field emission tip in your Titan machine here is well taken care of. There are some problems with the different, characteristics of tips. As I mentioned, thermionic tips are cheap, they're inexpensive. They're relatively low brightness, okay? LAB6 are brighter beams with more visibility. Field emission are the brightest, okay? On the flip side, go over to this end, thermionic tips can work in relatively poor vacuum. LAB6 needs better vacuum. Field emission needs really high vacuum, okay? So this is part of where the cost is, right? These are cheap and inexpensive. They work in lousy vacuum. They can take a beating, and they're not too bad. As we go better, hello, sorry, I didn't want to do that. As we go to a brighter source, which means a smaller probe, the requirements on the vacuum get better and better. So these are field emission guns are not typical machines that you use routinely unless you take care of them. Okay? The other characteristic about the different sources is the amount of current in the probe. So this is a function, this is probe size versus current. So the very large probes, the tungsten and the LAB6 have a lot of current and they're very big probes. The field emission guns peter out. As the probe size starts to get smaller, so for smaller and smaller probes, the amount of current decreases dramatically. So when we want really small probes, we tend to go to a field emission gun. So we have lots of current in small probes. Okay, how are we doing? 10:30. When did you want to take a break?
Another 15 minutes.
15 minutes. Okay, good. Okay, so we've talked about the electron sources. Let's talk about lenses now. Why do we need a lens? Okay. There are a lot of lenses in an electron microscope. So far, we've been just talking about the electron source, which is up here. Okay? There are a whole slew of lenses. We'll talk about the different lenses in a few minutes as we go through it. Skip this slide. Okay, so the TEM column, which is mainly what we're going to be talking about here, consists of an illumination system. We've already talked about the source. We have an illumination system, an image forming system, and then a projection system. So this makes the probe. We bring the probe to the sample. We magnify the image from the sample a little bit, the first image, and then the projector system gives us even bigger magnification or different operating modes. And that all goes down to a screen where we detect things. Okay, the illumination system, the role of the illumination system is to bring the probe, the electron source, to the specimen. Okay, and there are a lot of different ways of looking at it. We'll get back to this slide in a little bit later. Okay, that's actually in the wrong spot. Okay, actually this is in the wrong spot too. Okay, let me just see. Let me move forward here. Okay, yes, this is the slide I wanted. Sorry, those two slides were out of order. That's what happens when I put things together late at night. All right, so why do we need a lens? Okay, let's ask ourselves. We have a beam of electrons, right? The problem is we have our electron source, and we've turned it on. I don't care what kind of electron source, any electron source. The electrons are emitted from the tip, and they go off in all directions. So what we want to do is we want to bring those electrons, rather than scanning them in a large area, down to a small area. And that's the role of the lens. Okay? Lenses have a lot of functions. One of them is to take a source and bring it down focused to a point or to an image. Okay? In electron microscopy, we tend to use something called an electromagnetic lens. Why? Because that's the easiest type of lens to build. Okay? There are also electrostatic lenses. We won't be talking about those today. How does a lens work? It's very simple. Most of you have already had your basic physics courses. You know something called the Lorentz force, right? So what happens if you have an area of a material which has either an electric field or a magnetic field in it, and we have a charged particle going through that? The Lorentz force, whether it's an electrostatic Lorentz force, the force is equal to charge times the electromagnetic field. If it's an electromagnetic lens, it's the velocity of the charge times the velocity of the particle crossed with the magnetic field. Basically, what's happening is you have a charged particle going through a region of space where there's a field, either electric or magnetic, and that causes the beam to deflect. Okay? The nature of how that deflection goes is proportional to the size of the electrostatic field or the magnitude of the magnetic field. And that only exists over the region of space that the field is extending. So once we get out of the region where the field is, the particle keeps traveling in a straight line. Okay. Lenses in an electron microscope are formed by coils of wire. Okay, we have loops of wire. You've all made electromagnets, I'm sure, at some point in your time. Taken a wire, wrapped it around something, put voltage across it, and you made a magnet. You've made a lens when you've done that. Okay? In the case of an electron microscope, we have lots and lots of windings going around. So you can see the windings here. The windings are so finely spaced here you can't actually see the individual wires. Okay? We run a current through that, which creates a magnetic field in this direction. Okay? You also know that if you put a piece of metal inside a winding, you can intensify that magnetic field. So all microscope lenses have a pole piece, which is a piece of metal. Usually it's an iron cobalt alloy to increase the flux and concentrate the flux in a small area. Okay, there are lots of different types of lenses. There are condenser lenses, objective lenses, and there are different types. We have a symmetric lens where these are the windings, and these are the pole pieces with a small hole down the middle that the electron beam comes down. We can have snorkel lenses, and we have quadrupole lenses. Okay. What's important about the lens, just to give you a sense of it, is that right in the middle of the lens, there's no focusing action, okay? All of the key parts of a lens happen right at the very tip of the pole pieces. Why is that? If it's an electromagnetic lens, you have a particle going in one direction, forward. You have a Lorentz force. What is the Lorentz force? It's when the velocity of the particle is perpendicular to the magnetic field, okay? At this part of the lens, the magnetic field is parallel to the velocity of the electron. There's no focusing action done here. All the focusing action is done right at the tip of the pole piece where the lens, the magnetic field is actually bending slightly. Okay? That's where your Lorentz force is. Why do I make a point about that? Because at some point in your life, you will be interacting with your microscope. You will have a pole piece. What you don't want to happen is you don't want anything to happen to this area. If you have think of it, your sample is going to be sitting in between the pole pieces. The key area is right here, right at the pole piece, right at the entrance. I don't care what happens here. I don't want you to affect this shape right here. I don't want you to chip it, to bend it, to do anything to distort this, because that's where the key features of the magnetic field are. So you always most microscopes actually have safeties. They have safeties so when you get close to hitting a pole piece, it'll stop you from doing it. You can always defeat safeties. That's unfortunate. So this is the key area that you always have to protect on a microscope. Okay, we've already seen these images before. Let's skip forward. How do we get magnification with lenses? Okay. Magnification is quite simple. We have an object. We do a simple... Sorry, I keep doing that. I didn't realize this was a touch screen. We have an object. The rays come past the object through a lens and focus to a point. The magnification is simply the ratio of the distances of the object space to the image space. So magnification is just B over H in this case. The closer, the difference in the ratio between A and B is what gives you your magnification. All right, so if we have one lens, we have one magnification. All microscopes have multiple lenses. Why? Because we need to get higher and higher magnification. What do? We magnify the first time, magnify the second, magnify the third. So we stack lenses one on top of each other to get increased magnification. By controlling the strength of the lens, we control the focal length, which is control the distance between A and B, and control the magnification. So when you're changing magnification in a microscope, what are you doing? You're changing the amount of current in different lenses, and that's giving you different focal lengths and hence giving you different magnifications. Most transmission microscopes today have an objective lens, which runs at constant power. You usually don't change that one at all, but you have several post-specimen, post-objective lens lenses, and that gives you your magnification. All right, so we've magnified something. The important thing to do when you magnify an image in your electron microscope is to know, what's my magnification? Very important. Whatever you do, you will see a knob on your microscope and it'll say magnification 10,000x, 20,000x, 100,000x, 1 millionx. That's fine. It's an order of magnitude. Don't trust it. Okay? What I want you to do is learn how to calibrate your microscope for your conditions. Okay? And what you will do is you will have some sort of standard specimen with known spacings, okay, one of which you can buy. It's called a replica. It's a diffraction grating. We know exactly, in this case, 2160 lines per millimeter. We can put this in the microscope. We take an image at whatever magnification is. We measure that distance. We know what it is, okay? And you can then calibrate the magnification. The number on the microscope will never be correct. It will always be wrong. It'll be close. Manufacturers go to great efforts to make it approximately right. You go to 10,000x and you say, yeah, that's about 10,000x. Okay. But if you need to do an accurate measurement of anything that you're doing, I want you to go in, make sure you've done the calibration. Okay? Make sure you know it. And just because you've done the calibration, there's certain key things in it. The specimen height has to be right. Everything has to be right. You'll learn that when you do your training of the microscope. You should do a calibration for yourself, store it, and keep it with your records. Okay. That's good for low resolution, for relatively low resolution, up to 50, 60,000 times, something in that range. But once we start getting to very high resolution, what you're going to need is another calibration. Okay? When you're up at 1,000,000x, what do you use as a calibration? Those lines at 2160 lines per millimeter are miles apart. We'll never see them. So what we do is we prepare internal standards. Use a pure element. The typical thing that's used nowadays is silicon. You can get pure silicon. We can make silicon samples. We know the crystal structure of silicon. We know the lattice spacing of different atomic planes of silicon. What you're looking at here is a single crystal of silicon. These are atomic columns. We know the spacing of these planes, and so I can use that for high resolution calibration. Again, learn how to make you need the sample. Can you buy this? Yeah, you can buy silicon specimens if you can't make one here. But learn how to put it in, get a microscope, get an image, and do a calibration. The other thing we do quite often is you move the beam around. Okay? There's something called beam control, beam deflectors. Okay? How do beam deflectors work? Well, you already know how they work. They use the Lorentz force. What they are coils, okay? Either above and below the objective lens. They're the same coils that you have here, except turned 90 degrees. They create a magnetic field going back and forth. And what does that do? It simply deflects your beam back and forth. So it's the same as doing this, but except we're not really doing too much focusing because the field extends very small. So all it does, the beam comes in and deflects. Okay? So you have deflectors. These deflection coils exist in many places. They also do several functions. One can be just a simple tilt of the beam. We can bring the beam in. We use two coils to do a beam tilt. One beam comes in, tilts it a little bit. Second beam tilts it even more. Okay? We can also we do multiple tilting, or we can do just a simple deflection. And to do a simple deflection, what we do is we still need two coils. We deflect once and then deflect back. So these coils are working opposite directions. Okay? Astigmatism is a problem in everything, not only for people with bad eyes. We can never make a perfect lens. There is no such thing. Okay? All lenses, even if we machine it as accurate as we can, will always be slightly asymmetric. What does that mean? Because it's slightly asymmetric, we will have electrons that are focused to different points depending on where they're coming through the lens. So what you will have is a disk of confusion. So in order to fix that, we use something called a stigmator. And a stigmator is a set of coils, similar to deflection coils, that are surrounding the sample. And what they do, they cover a very large area. And what we can do is compress or expand the beam. Okay? We can have lots of different kinds of stigmators. We can have 4, even 8 to surround the sample. Okay? How do you know you have an astigmatic beam? Well, just look at it. This is a beam, a focused beam, which is astigmatic, right? It's not round. It should be round. What we do is we use the deflection coils, using the stigmators. We're squeezing and expanding the beam to make it round. Okay? That's what a stigmator does. And all just a simple set of coils. Okay? How about astigmatism in our image? Okay? Again, we've got a lens. We formed the probe. We made a nice round probe. Now we hit the sample. Now there's other lenses past the sample. You will see astigmatism in your image. And how can you recognize it? There's a lot of ways to recognize it. The simplest way is when you look at a focused image, and we'll tell you what a focused image is in a minute, and we look around the edge of the image, you will either see a dark line or a bright line. Okay? And you look at this one in particular, you notice it's asymmetric. Here it's really black and dark, and all of a sudden it changes white. Okay? The effect that we see here is called a Fresnel fringe. We'll talk about that later when we talk about imaging, but the fact that it's not symmetric, going all the way around, tells you you've got astigmatism. What your stigmator will do, just like the probe stigmator, now we have an image stigmator, a set of coils. What we can do is adjust that stigmator, and you notice I've adjusted the astigmatism here, which is asymmetric, to be perfectly symmetric. Okay? Learn how to do that. This is generally done at low magnification. At very high magnification, we're looking at an image, and How can you tell if we're astigmatic here? You really can't. If your eyes are trained and you learned how to do it, you can look at the image and say, yeah, that's definitely astigmatic, because what I do is I'll look at this and I see a little bit of streaking this way. And what I want to do is I don't want any of the streaking. This is the same area that's astigmatic, and this is corrected. Okay? Now, I can look at that and tell the difference. Nowadays, there's an easier method, rather than straining your eyeballs, and that's by taking a Fourier transform of that structure. If I do a Fourier transform of an image that's astigmatic, I will get a set of concentric rings that are elliptical. I can then use my stigmators to make those ellipses round. Okay, so I've gone from an astigmatic image to stigmated images. This method only works at high magnification. At lower magnification, you use the other method. Okay? The other thing Fourier transforms are also very good with is they're very good for showing you problems in the instrument. We'll look at this image, and you say, is this astigmatism? Is she streaks? Okay, well, what was happening is the sample's moving. Okay, so we're seeing streaks here. When I look at a Fourier transform of something that's moving, I see bars perpendicular to the motion direction. Okay, so we can see those large bars. When the motion is minimal, it's just round again. Okay. You can also look for problems. If you have a turbo pump on your system, I know you do. Turbo pumps, vibrations in the room, noise in the room causes vibrations. This is a turbo pump motion. You'll notice there's a cutoff here in the Fourier transform. That's due to the turbo pumps vibrating. When we cut it down from full speed down to slower speed where it's not vibrating, that goes away. Cell phones. This is an image in our atomic resolution microscope. Cell phone was off, cell phone was on. And nobody was talking. The cell phone was just on. So there was an electromagnetic, the communication from the cell phone tower was penetrating the microscope room, causing electrical interference in our power supplies. So don't have your cell phone on when you're working in the microscope room. Okay, I think this is a good time to take a break. Let's take what we used to call them bio breaks in the States, and then we'll continue with apertures versus lenses. Okay, good. So we'll pick up here, and how long do you want to take a break for?
20 minutes.
It's up to you. You pick it.
20 minutes.
20 minutes. All right, we'll just meet back here. Are we set?
Yeah.
All right. Everybody, if you want to get a copy of the PDFs, send an email to Barun. He's in charge, right? Where are you? There he is.